A common mistake in system design is simply guessing the number of partitions. Guessing leads to either massive waste or performance bottlenecks down the road. Consider a system handling 100,000 events per second, with each event at 400 bytes. This results in a raw throughput requirement of 40 megabytes per second. We don't guess. We calculate based on the specific throughput limits of our brokers and the processing capacity of our consumers. The decision process flows through these constraints to find the optimal partition count. Remember that in distributed streaming systems, partition counts are notoriously difficult to decrease once your data has started flowing. Design with growth in mind. To calculate throughput, we start with our core requirements. If we have 100,000 events per second, and each event is 400 bytes, we need to determine our total data ingress per second. Multiplying these values gives us 40 million bytes per second. Converting this to standard storage units, we arrive at a baseline of 40 megabytes per second. This is our raw data requirement before factoring in any infrastructure or networking overheads. This baseline is essential for capacity planning, serving as the starting point for scaling your brokers and ensuring the system can handle the expected load. Replication is a core component of distributed systems. It ensures data reliability. By default, Kafka replicates each block 3 times across different nodes in the cluster. This has a direct impact on performance. If your application sends 40 megabytes per second of data, a replication factor of 3 means the cluster must handle 120 megabytes per second of internal traffic. This is vital because brokers are now burdened with significant extra I/O. They must manage the overhead of synchronizing follower logs, creating increased pressure on both disk and network bandwidth. Higher replication ensures high safety, but it comes with a proportional increase in infrastructure requirements. We must account for network protocol overhead. Applying snappy compression typically yields a 40% reduction in payload size. This allows us to establish a conservative 40 megabytes per second target for our throughput baseline. By calculating the net throughput after compression and adding necessary buffer for protocol overhead, we arrive at our stable target of 40 megabytes per second. The consumer side is a critical bottleneck. A single consumer typically processes about 2 megabytes per second. If our system target is 40 megabytes per second, we require 20 active consumers. Because Kafka maps exactly one partition to one consumer thread, the number of partitions must be at least equal to your consumer count. Therefore, to support 20 consumers, we need at least 20 partitions. This diagram illustrates the distribution of data across partitions. By balancing the load across 20 partitions, each consumer operates within its capacity, ensuring stable stream processing without falling behind. In real-world systems, traffic is rarely static. We must account for both sudden bursts in requests and consistent annual growth to ensure our partitions don't bottleneck. Applying a 2x peak multiplier immediately doubles our need to handle spikes. Then, adding a 50% growth buffer provides the headroom required for long-term scalability. This shifts our initial estimate from 20 partitions to a robust range of 30 to 40. Planning for these factors prevents costly repartitioning operations later on. By designing for 30 to 40 partitions, you build a resilient, future-proof streaming architecture. When scaling Kafka, selecting a partition count is not just about math, but about even distribution. Choosing 52 partitions is an excellent choice for a cluster of 12 brokers. By dividing 52 by 12, we get 4 with a remainder of 4. This means 8 brokers host 4 partitions, while 4 brokers host 5. This is nearly perfectly balanced. Furthermore, 52 is highly divisible. This property provides flexibility, allowing you to easily adjust your cluster topology or expand the number of brokers in the future while maintaining a balanced load. A consumer isn't just one thread. Data ingestion involves pulling records, submitting them to a processing pool, and committing offsets. This loop is the foundation of our throughput. With a 30 millisecond database write latency, a single thread can only process 33 events per second. It becomes a major bottleneck. To hit a target of 2,000 events per second, we cannot rely on one thread. By distributing work across roughly 60 concurrent worker threads, we overcome the latency and achieve the required scale. With our 52 Kafka partitions identified, we deploy exactly 52 consumer pods. This one-to-one mapping ensures optimal parallelism for our processing needs. We define our resource footprint precisely. Each pod requests zero point 0.5 CPU cores and 1 gigabyte of RAM, with the ability to burst up to 2 gigabytes during load spikes. By declaring these requests, the Kubernetes scheduler intelligently places these pods on nodes with sufficient capacity, ensuring our processing remains stable. To determine the capacity of a node, we start with the hardware specifications. An M5.2X large node provides 8 CPU cores and 32 gigabytes of RAM. We must account for system overhead, including the kubelet, operating system, and essential daemons. This consumes a portion of our resources, leaving about 28 gigabytes available for application pods. Given our resource requirements per consumer pod, this specific configuration supports a density of 9 pods per node. Balancing throughput with resource headroom is critical for preventing evictions. To support our calculated workload, we have determined that we need a total of 52 consumer pods to handle the incoming data stream. Assuming a standard pod-to-node density for our cluster, these 52 pods necessitate a minimum of 6 physical or virtual nodes to operate efficiently. However, in production environments, high availability is mandatory. We must ensure redundancy so that if a node fails, our system remains operational. By doubling our base count for redundancy, we arrive at a final deployment size of 12 nodes. This provides the necessary headroom for failover and maintenance. To estimate our total infrastructure cost, we first sum our required nodes. Based on our throughput calculations, we need 12 consumer nodes, 12 broker nodes, and 6 API nodes, bringing our total to 30 nodes. Infrastructure costs are typically driven by server capacity, power, and cooling. Here we see a typical cost distribution where servers represent the largest expense. At a base cost of $900 per node per month, we arrive at our annual infrastructure spend. After factoring in storage and interregion data transfer fees, we estimate an annual budget range of $150,000 to $200,000. In a system design interview, you are often asked how to adapt to sudden change. Imagine your system handles 100,000 events per second. How do you scale to 1 million? To reach 1 million events per second, we apply linear scaling. If one partition handles 50K events, we increase our partition count tenfold to maintain the same throughput per unit. However, scaling partitions linearly reveals new hardware bottlenecks. As the cluster grows, network I/O and disk throughput become the new constraints. When defending your design, focus on the cost of managing a larger cluster and the increased metadata overhead in Zookeeper or controller nodes. When scaling Kafka clusters, certain architectural choices often lead to performance degradation. Avoid these 3 common red flags to keep your system stable. First, avoid creating more consumers than partitions. Kafka assigns partitions to consumers one-to-one. Extra consumers will sit idle, contributing nothing to throughput. Second, never push more than 10 megabytes per second through a single partition. Exceeding this triggers significant replication latency and broker instability. Finally, beware of under-provisioning your Kubernetes pod resources. Insufficient memory or CPU requests inevitably lead to pod eviction and out-of-memory errors during spikes. Proactive resource planning is the only way to prevent these bottlenecks and maintain high system reliability. In Kafka design, the rebalance time is a critical performance indicator. A core threshold to maintain is the 5-minute rule. If partition rebalancing takes longer than 5 minutes, your system is likely too fragmented. When design is too fragmented, you observe metrics degradation. Watch your request latency and error frequency. High partition counts force the broker controller to work harder, delaying recovery times significantly during broker restarts or network partitions. To ensure system health, keep your metrics lean. Monitor your partition per broker ratios strictly. If you find rebalance operations dragging, consolidate partitions or reconsider your throughput per partition strategy. To excel in your system design interview, you must master the core mental math. Always remember, throughput equals events per second times event size divided by 1 million to find megabytes per second. You are not expected to know every variable, but you are expected to justify every assumption you make. Whether it is storage duration, peak to average ratios, or replication factor, be ready to defend your reasoning. Finally, synthesize these calculations into a cohesive architecture. Think about how your estimated throughput dictates partition counts, node allocations, and your overall data flow from clients to the database. Confidence in your numbers turns a guessing game into a structured, engineering-led conversation. Prepare your checklist, know your limits, and design with purpose. First, calculate throughput in megabytes per second by multiplying events per second by average message size, then dividing by 1 million. Next, determine the required number of partitions based on the throughput limit per partition. Finally, pods scale with consumer capacity, and nodes are determined by memory requirements per pod relative to total host capacity. These fundamental equations ensure your Kafka cluster is sized correctly for your specific performance demands.